Hi, my name is Katerina, and today I will be talking to you about the creation and expansion of an inclusive and diverse lifestyle factor ontology for biomedical text mining. There are vast amounts of biomedical knowledge available only in the form of unstructured English text, otherwise known as the scientific literature. And the knowledge of associations between lifestyle factors and diseases is important for the interpretation of clinical data, among others. However, there is no knowledge base available that has this information. So in order to be able to get that information out of the scientific literature, what we need to do is use text mining. And there are some prerequisites for text mining. First of all, we need to be able to do named entity recognition of diseases, then do named entity recognition of lifestyle factors, or I will call them LSFs from now on. And then that will allow us, since we have identified the disease and lifestyle factor entities in the text, to do relation extraction to find the associations between these entities. But from these three prerequisites, the only thing that we already have is the named entity recognition of diseases. So what we need is first to do named entity recognition of lifestyle factors. And the suggested approach for that is to create a dictionary of lifestyle factor names based on an ontology. However, no such ontology that covers the entire spectrum of lifestyle factors is available, since all existing lifestyle factors ontologies are limited in category coverage. For example, there are some lifestyle factor ontologies for food or for smoking, but nothing that can cover both. So the first step for us is to create this ontology and then do the dictionary-based named entity recognition that I mentioned before. To this end, we developed a prototype ontology of lifestyle factors with 9 main branches to encapsulate the diversity of all of these factors. The terms were added in the ontology manually as a result of looking into the literature, questionnaires, previous ontologies, and brainstorming at this stage. For this reason, this list is neither exhaustive and it has a high level of bias. So in order to alleviate these two issues, we decided to move forward with automatic ontology enrichment with deep learning. And in order to do that, we need a deep learning-based language model, and we went with a domain-specific one, in our case, BioBERT. And what we did, the first step was to train a BioBERT model to detect lifestyle factors, then find new terms from the scientific literature which are not present in the current version of the ontology, classify them as belonging to one of the pre-existing ontology branches, or examine whether new branches should be added, evaluate whether these terms are synonyms of existing terms or new terms, and finally add them to the lifestyle factor ontology. But what could serve as the source of these new terms? After brainstorming a bit, we came up with the idea of looking at Wikipedia titles. But this sounds a bit weird, and we were like, is it really a good source of new terms? And in order to check that, what we did was check the overlap between names in the current version of the ontology, the manually created one, and names in Wikipedia titles. And we find that this coverage was high enough and sufficient to move forward. The next thing that we needed was training sets to fine-tune, so do the supervised training of BioBERT. And we needed both a positive set and a negative set. And the positive set was examples of context around lifestyle factors from the literature, while the negative set was examples of context around other entities. And here I want to bring your attention to the word context. We don't want to model to learn how the current lifestyle factors look like, because that way it will only detect the same things. But what we wanted to learn is how the context around it looks. So for example, if I have a sentence that says people who quit X have a lower risk of lung cancer, I guess as a human you can understand that it means probably smoking, and then that is a positive example for us. Smoking is a lifestyle factor, but when a sentence says when X becomes mutated, it loses its function, resulting in abnormal cell proliferation, I guess you can also understand that this is a gene, and in this case P53. So we don't want the model to learn the names, we want to learn how things look around the names. In that sense, it can predict new names that we don't have already. So after training the model, we received a very good accuracy for the best model, around 95%. And then we used this model to predict new terms, and after doing some aggregation of the scorings and looking at top level terms, we identified almost 500 new terms for the ontology, which gave more than 5 million matches in PubMed. But I mentioned before that we want to do relation extraction. So the simplest form of relation extractal is simple co-occurrence. So we look at names that sew up together a lot. And in our case, we had almost 500,000 associations based on co-occurrence, and many of them were high scoring, almost 50,000. And these high scoring ones, after some random sampling and checking, we saw that provided us for some related pairs. But the other thing that we found at these steps is that there are some names in the ontology that are still problematic. So we decided that we need to do some cleanup and further expansion, and this work is currently in progress. But let's go back to the associations. What is the nature of these associations? In contrast to gene disease association, the nature of associations between lifestyle factors and diseases is not always causative. For example, in this case, exposure to radiation can be used both as a treatment for a disease, but can also cause a disease. So the simple co-occurrence-based text mining doesn't give us a lot. So in the future, what we plan to do is use deep learning again to do relation extraction. And in order to do that, we need to manually annotate disease lifestyle factor associations, train a deep learning-based model, again, a BioBERT model, for example, extract associations with specific type from the literature, and create a knowledge base of disease lifestyle factor association. I would like to thank everyone who contributed to this work, and thank you for your attention.